I'm Dr. Deepak Chopra, and it is my great pleasure to be having this conversation with my very good friend and oftentimes worst critic, physicist Leonard Mlodinow, whom I met at a debate, actually, that happened at Caltech, and Michael Shermer, who's part of this conversation, and I were having this conversation then, much more contentious, but it all ended up in a good friendship. And our book, War of the Worldviews, the worldview of scientific materialism and the other worldview, for lack of a better word, the worldview of non-dual consciousness. But Leonard has very kindly agreed to be with me here so we can have this conversation. This is his book in paperback, which is out right now, The Upright Thinkers, The Human Journey from Living in Trees to Understanding the Cosmos. And the Washington Post says, an entrancing tale of scientific history. And you have a quote here from many other people, including Stephen Hawking, I believe, right? Who was your co-author in Grand Design. So,
yeah, there it is.
So Stephen Hawking says, Mlodinow never fails to make science both accessible and entertaining.
There you go.
And
you
wrote The Grand Design with him too,
I did, yeah.
And then also A Briefer History of Time.
Right.
So I'm really privileged to have Leonard here. And incidentally, we're going to talk a little bit about my book, which is called You Are the Universe, Discovering Your Cosmic Self and Why It Matters. And even though I wrote this book with quantum physicist Leonard Mlodinow, we had Leonard actually go through the book to make sure that the science was correct, and he gave it a very close critical examination and made some corrections. So thank you, Leonard, for that too. So this book in particular, let's talk about this book first. What's it about?
Well, I explain in this book how we got to our current idea of the universe and our role in the universe. What is life? Where does it come from? And where does the physical universe come from? And how do we know these things? And so I trace our ideas about that all the way from when humans were basically apes living in the wild, through the invention of writing and arithmetic and philosophy and science to the modern chemistry, physics, and biology that we practice today. So I show how that all fits together and how the advances at each stage fit in with the culture at the time, and where all our ideas come from, and why we care, why humans, what is it about the human mind that cares about these answers?
So let's actually talk about that a little bit. So basically this is the evolution of
Scientific
ideas.
thought.
Scientific
ideas,
thought,
right.
Yeah. And that's fascinating. I read a book recently called Sapiens. Did you read that? Very interesting. What did you think of that book?
That was a good book too, and it was on a similar topic. Not as good as this book.
Of course. So this book is The Upright Thinkers. So where do ideas come from, Leonard?
Well, that can be answered on so many levels. On the most neuroscientific level, the ideas come from parts of your brain, especially the right hemisphere, if they're original. And
so how does the brain construct an idea?
Well, that's complicated. The brain is as you know, conglomeration of neurons which are highly interconnected, and they fire and they send signals to other neurons. And the best model that I like to use to understand how that works is to think of ants. You know, if you've all seen ant armies crawling around, and each ant is a very simple creature. It doesn't really know very much, has no idea what the ant colony is trying to do, but each ant follows certain rules when it crosses the path of other ants, depending on how many other ants are in its neighborhood, what chemicals the other ants might leave by, and then it changes its behavior based on that. And somehow, based on all this microscopic, or I would call that microscopic or individual behavior of all the ants, the colony is like an organism that accomplishes amazing things. It can build a bridge, for instance. So no ant is an architect saying, how do we build a bridge? And yet, based on these individual decisions of the ants, the whole makes a bridge. The whole reproduces and keeps
And
going.
the
from
whole
year to
is
year.
more than the sum of its parts.
Right, and that's the way our brain works. So our brain is a big colony of neurons which are interconnected in a far more complicated way than the ants. But from that conglomeration of neurons, ideas arise. Now you're going to ask, I know.
No,
You know, where are the
we-
ideas? Who is getting receiving the ideas?
we don't have to go there now.
Okay,
We're
good.
talking about your book, right? We're talking about
Well,
your
so the
book.
thing about people and
Yeah.
humans is that we are different in many ways from other creatures. And people like to say that we're different, that we do this and they don't do that. And in this book, I talk about how a lot of that isn't really true, that we do this and they don't do that, but it's a matter of degree. And one of the things that humans are really different at, or have a much greater degree, is curiosity about the world. So if you do experiments, say even with a chimpanzee in the lab versus a human child, and you give them some weird arrangement of blocks, let's say, that because of the way the scientists weighted the blocks, they don't act normally, like according to Newton's laws, they don't act the way things do in everyday life. You can see that the human child is much more curious about why that is than the chimpanzee is. So through experiments like that, we can see that people are really much more curious about their surroundings, and that curiosity is what drives us to understand the world and to do science.
So in a sense, the cosmos and the brain are kind of complementary to each other, right? I'm not using the word complementarity the way physicists
Well, I
do.
don't. Okay,
But you need a human brain.
brains obviously are very interested in understanding the cosmos. I don't think the cosmos really cares much about the human.
But you
brain.
need a human brain to know the cosmos.
No, I mean, bats have their own understanding of the cosmos. Ants have their
Oh,
own
good. So
understanding.
there are
of it.
many
Even my
kinds-
friend Christoph Koch, the neuroscientist, would say a thermostat has its own understanding of
Okay,
it.
so
And it's a
that-
very simple one in the case of a thermostat.
I
Is
would
it
li-
70 degrees or below 70 degrees?
I like that because then that's another multiverse explanation, right? There are as many universes
Well, as concepts
as
as there are individuals.
there are species of consciousness
Or individuals, yeah.
or individuals. Well, there I totally agree with you, that there is no single universe.
I'm glad we agree on something.
That there's no such thing as a universe. It's a concept like anything else. It is a model, right? The human universe.
The universe that you read about in books like this or like yours is a model. Yeah,
Yeah.
It's not the actual universe.
Yeah.
The actual universe is much larger.
Or much more inexplicable. It's either a human experience or the one that's larger, the chaotic inflation one, is in human imagination, mathematical imagination, right?
Right.
Yeah. Okay, so this is really good because at least on some things we do agree. You can't kill ideas, even though the organism that came up with the ideas dies. Ideas can outlive the physical structure through
Well,
which
they can. I still fly on planes even though the Wright brothers are dead.
That's right. That's very good. Who should read this book?
Everybody.
Everybody should
Everybody
read this book.
should
You
read
get
this book, especially in today's world, because technological and scientific issues are very important in politics and society today. And this explains where they come from and the kind of thinking that scientists use to come up with their ideas. And it explains really what we mean by a theory, or when we say that we know something in science, what do we mean by that? So if you read this, you'll get a much better understanding of that.
Should our president-elect read this book, or
Does
would
he
he
read?
understand it, do you think?
I think that our president is a reflection of a certain subculture in this country that doesn't care about what's true. And so I would like him to read
What's
this
closer to truth anyway, yeah? What's closer to truth anyway?
book, what the facts are
Yeah.
versus, because you can
Yeah.
argue what the facts are. So,
Yeah.
but if I would be happy. I'd
Okay,
be,
Mr. President-elect, do read this book. You'll get a lot out of it, and your supporters too. So let's come to my book, which you were so kind to correct. And we had a long conversation about some of these concepts with our friend Michael Shermer. But, you pointed out some errors, and I'm grateful to you for that. We had actually several physicists read it just to make sure that the science was as close to accurate as possible. And the first section of the book is 9 conundrums. And I just want your best answers on each of these, if possible. What came before the Big Bang?
So we don't know what came before the Big Bang, and we hardly even have a theory of that. Really, what we understand pretty well starts with the period that scientists call inflation, which is really, in modern physics, what the old idea of the Big Bang translates to is this period of inflation. And so the model that we have now is that the principles of quantum theory govern the universe, and that quantum theory tells you that that systems in a certain state of being aren't precisely in a particular state, but they have a realm of possibilities of being in many different states. And that's just one of the basic premises of quantum theory, is that that the properties of systems that we measure are not well defined, but there's a whole spectrum of properties any system can have. And when we go back to the early universe and apply that to the early universe, we see that means that the future of the universe from that early point can look in various different ways. There are various different quantum possibilities for the universe, and inflation is a theory that uses that idea to explain, and some more technical mathematical ideas of what's called quantum field theory, to explain how our universe started from a very short, very long time ago, for about, say, 10 to the minus 35 seconds. Before that, we don't really have much idea. But from there, we can do measurements. Inflation.
Is that the Planck epoch, which you don't have yet?
Around the Planck epoch. And we can do measurements of the early universe. We can do measurements of leftover, let's say, the afterglow of the Big Bang or of inflation, and compare it to the theory and see that the theory is on the right track, because there's some very detailed measurements that we do very precisely that actually match very well with this picture. So we have pretty good confidence that something like that happened back then. But before that, before that, everyone has their pet theory, including Stephen Hawking and I, which we wrote about in The Grand Design, but we don't really know, and I don't see right now that there's any experimental or observational data that has
chaotic
come in that
inflation,
can help us.
eternal
There are
inflation.
many theories of different versions of inflation. And
so, I'm not going to go through the 9 questions because it would take forever. We'll just stay with this.
We could, any good question could take up a whole interview in itself.
So based on this one question, what you're saying, that the fine structure of the universe is quantum in nature, right?
That we would say, the physicists would say, the dynamics, what defines how things interact with each other is governed by the laws of quantum theory.
Why does it look like this?
Well, okay, so the world that we all observe is what we call classical, and it's the macroscopic world that Isaac Newton was familiar with, that he described, and his equations describe it extremely well, which is why we have most of the physical structures around us here, and because they are based on his idea.
But do they arise from quantum phenomena?
Well, so that is a very sound physical theory of the macroscopic world, but around the end of the 19th century, we started to be able to do experiments that revealed effects that are happening on a microscopic level that we can't see with our naked eye or hear or touch. And we learned that everything like this wood and this building is made of smaller particles, atoms, electrons, protons, and inside them we eventually learned there's quarks and there's other elementary particles. And that those all obey a different set of laws, which were discovered between about 1900 and 1925. And those are the quantum laws that we believe all of nature follows. And one thing that physicists have done, and I've written papers on this, is to explain how from those laws, you can derive, when something is made of many, many particles, how those laws lead to the laws that Newton saw. So if you have the microscopic laws of quantum theory describing an object, but you step back and you say, well, we don't see all those little particles, they're too small, but they're interacting in some way, how can we explore what the laws are of that bigger object that's made of these made of these smaller particles and their interactions, and what laws would they follow? And we can show that how the way those quantum laws interact to produce Newton's laws on a macroscopic level.
Got it. But now, two questions from that. Those fundamental particles, all of them, quarks, etc., electrons, photons, protons, neutrons, are also waves, right? They have a dual nature.
So people say that things are on the quantum level are both particles and waves. So you don't see that on Newton's laws level, because when they interact, that behavior goes away. So and when people say that they're both particles and waves, that's not really precisely what is going
So
on.
what's
going on is that when you look at their behavior, there are situations in which a human being who's used to seeing water waves would go metaphorically, oh, that reminds me of a water wave. And there are other situations in which we observe the results of the experiments, and oh, that reminds me of when I throw a baseball. So when the experiments look more like a baseball, we go, oh, that's a particle, and the other one we call a wave. But those are just
metaphors.
Metaphors are thinking tools because physicists, even though we work with mathematics, we all make pictures in our heads to understand what's going on. Yeah. Pictures are based on stuff that we see in the real world, not stuff that you can't see.
But those waves are often referred to as waves of probability, aren't they?
Well, so when we look at the experiments, sometimes we see effects like interference, which remind us of how waves behave, light waves, let's say, or water waves, okay? That is caused by the fact that, if you look at the mathematics, that the objects are being described by equations that are reminiscent of wave equations, and they describe not the probability, but a pre-probability of we call the amplitude for these things. So if you look at an electron, its probability amplitude, its wave function, describes, it can be used to determine its probability of being someplace at some time, and that is described by equations that look like wave equations.
And where do those exist?
Where do what exist? The electron or the equations?
The equations.
The equations usually exist on paper or a blackboard.
Before that?
Before that, they were envisioned in a physicist's head, but they didn't exist the way you'll see them if you look at an equation.
So they exist in mathematical space, right?
They existed in the form of some of the state of some neurons in a brain that then translated them to writing to put them on the blackboard.
Okay.
Just think of the ants again. So when the ants are in this situation, when the millions of ants are in a certain way, that's Schrodinger's equation.
I'm not. And I'm not a scientist of the stature that you are, but would you agree they exist in mathematical imagination?
Sure.
That's another model.
Oh yeah, I'm not one who believes that Schrodinger's equation, for instance, in quantum mechanics is a concrete reality. It's a model that we made. I'm sure there's very smart aliens somewhere flying around.
Last time I looked at the interpretations of quantum mechanics on Wikipedia, I actually sent this to you, and you helped me kind of think it through. There were over 20 interpretations of quantum mechanics. So the quantum mechanics itself is a mathematical calculation, right?
Well, quantum mechanics is a theory, and it's expressed in terms of equations and rules, rules for how you apply the equation.
And what are the 20 interpretations?
Well, there's only 2 or 3 that anyone ever talks about. I mean, everyone has, I guess, if you go on Wikipedia, there's, I'm sure,
20
you could probably find 20,000, but the main, there's the original interpretation, which was the Copenhagen interpretation. This is a lot of technical stuff to get into, but that is one that you're interested in because it says the observer is outside of the system. It depends on a classical observer looking at a quantum system, so a macroscopic person, or not even a person, it could be a book making measurements on a microscopic system. That's one that is, it's simple. It's not one that people really take too seriously today because we know today that there's no need to make a separation between the classical world and the quantum world. And then another famous one is the Everett interpretation, which says that when these different probabilities happening, so before an interaction occurs, there's only a probability of it occurring this way or that way. And after it occurs, if you measure it, then it happened one way or the other, right? So what's going on? And it says that at each point of interaction, there's a branching in the different universes. In one universe, it happens that way, and one it happens that way.
We happen
so
to
these are the interpretations of quantum mechanics are philosophy. And I know you say in a very derogatory way that most physicists say, shut up and calculate. The lights that you have there, the cameras that you have, and the microphones, they all come from shut up and calculate. If we sat around wondering which philosophical interpretation was the right one, we'd be still, working with an abacus and writing on papyrus.
I totally agree. For practical purposes.
So the scientists don't really care because all these different... Wait, but let me just say one other thing. And I know I'm talking a lot, but usually you do, so I'm just getting my revenge. None of these different interpretations have any effect on what the theory says will happen. So the predictions of the theory are totally independent of these interpretations. So these are for philosophers to debate about, who are interested in what's the nature of the universe on some metaphysical level. And for physicists, they're worried about, does the theory work? So
yeah, the theory works. I trust the theory to give us this representation, that people are seeing. I trust all those theories to take a jet plane to India. I trust my life with it, so I don't argue about that. But I do want to know how these photons that are now being reflected off us, right?
They're not being reflected.
They're reflecting off.
Well, they might be absorbed and another photon re-emitted.
Okay, the photons, some are reflected, some are emitted. Finally, they get to the brain, and we see this. How?
So
how do we experience this?
You get about 10 to the 10th, bits per second of data onto your retina. About 10 to the 4th bits of data get transferred through your optic nerve to the primary visual cortex. Your consciousness can handle about 50 per second. And so what happens is the electrochemical impulses are being sent around, filtered, and they eventually make a picture in your brain. And by the way, you always say that there's no picture of what you're seeing in your brain, but that's not really true in some sense, because if I look out at this scene, then let's say that light will be geometrically represented in my brain to one side of where that light is represented. So there is some geometrical fidelity to the way things are represented in your brain, but it's certainly not a postcard of what you're actually seeing. Now, what you're asking is a different question. I know, because I know you. You're telling me, who is it that's seeing that? How are you getting that experience? And to that, I have a very simple answer. I have no idea.
So I was reading up the other day on a Polish mathematician by the name of Alfred Korzybski. Have you heard the name? Okay, so he was in the 40s, 50s, and he's famous for having coined the expression, "the map is not the territory." And I'll send you some references on him. And in his papers, he claims something that you hinted at, that by the time information gets to the brain, or data gets to the brain, it goes through 5 levels of abstraction. So edit 1 is when the photons hit the retina. Edit 2, when the chemical reactions in the retina send an action potential to the brain. Next edit, when that translates into electrochemistry, the brain, and then the receptors, and so on. Which means what we're experiencing is an edited form of reality, right?
Right.
So what is reality then?
I don't know. My job as a physicist is to tell you what's going to happen in reality.
What our perception of reality is. So just a simple question, is our perception of reality reality?
Well, most scientists would say, first of all, they would say, I don't want to talk about it, it's pointless. And then if you give them enough beer or vodka maybe, then they'll say, yeah, well, I think that our perception of reality is a direct reflection of something that's out there. It's filtered through us as organisms, but it's direct reflection. I'm less of that type. First of all, I take more vodka to make me talk about it. And secondly, I'm less, I think, of a believer in that, how direct that connection is. I always think about how would a bat see the world, and colors probably meaningless, form have a different meaning. I mean, think of an alien that would come here who's so far ahead of us that we're like a bat to it. Its thinking, I doubt, is in terms of the same concepts and sensations and feelings that ours is. So I think that we're being very self-centered to think that what we see has a direct connection to what's out there. It's a construct that human organism created over millions of years of evolution in order to survive in that reality, whatever it is.
So that's actually one of the tenets of this book, really. It addresses what I call the human universe, which is a human construct of something more fundamental. And for lack of a better word, I call that awareness, consciousness, and the experiences that we have in consciousness that we interpret through a scientific model as this, or the sound of that plane, or the plane itself. And not that we know the answers, but I do think you and I both agree that we really don't know how we experience anything. Thanks, Leonard.
Thanks, Deepak.